Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is called Integration Strategy and Something Clever. As always, be an attentive learner while watching these videos. By way of introduction, I talked to a student who talked about understanding what problems are, so I actually wrote this lecture based on their suggestion. So integration certainly is more challenging than differentiation. In finding the derivative of a function, it's obvious which differentiation formula to apply, but it might not be obvious which technique we should use to integrate a given function. In fact, there's often more than one way. Until now, we've studied a technique in a section, and pretty much most of the problems work that way. So we talked about substitution, integration by parts, partial fractions, and a bunch of the trig things that we did. But in this section, we present a collection of miscellaneous integrals in random order, sort of like you're going to see on a test. And the main challenge, or at least the key first step challenge, is to recognize which technique or formula to use. Now, there's no absolute rules, but we do give some advice about a strategy that you may find useful. Now, a prerequisite for applying this strategy is a knowledge of the basic integration formulas. So you want to know this table cold. And most of these really should be memorized. They're not going to be provided on a test for you. It's useful to know them all, but the ones marked with an asterisk may be derived. So here is a list of formulas of things that we've talked about before. Now, when I say we've talked about them before in Calc 1 and Calc 2 thus far in College of DuPage, I guess I would say that problem 15 and 16 we haven't talked about yet, but we will soon. And these could be derived from other things. This could be derived by partial fractions, and this could be derived by trig substitution. And so, but anyway, having all these in mind is an important first step. Now, once you have armed with these basic integration formulas in memory, if you don't immediately see how to attack a given problem, then here's some of the strategy that I would perhaps recommend. Simplify the integrand if possible. Sometimes the use of algebraic manipulation or trig identities will simplify an integrand and make the method obvious. Here are some examples. This might look difficult, but if you use algebra and distribute this, you get something that can be integrated easily, term by term. This might look really complicated, but if you change everything to sines and cosines, you see that it becomes an easy integral to do. And here you could either let u equal sine theta, or you could use the trig identity sine theta cosine theta is equal to 1/2 sine 2 theta d theta, but either way, this is now easy to do. This one, if you use algebra, just squaring that all out, you'll get sine squared plus cosine squared is 1, so you have 1 plus, and then this is 2 sine x cosine x, which is actually sine 2x, so this becomes a very easy integral as well. A second approach, look for an obvious substitution. So try to find some function u equal g of x in the integrand whose differential du g prime of x dx also occurs apart from a constant factor. And you can always fix up a constant factor. For example, if you were faced with this, the indefinite integral of x over x squared minus 1 dx, you can notice that if you let u be x squared minus 1, then du is 2x dx, so you can use this substitution instead of working this by partial fractions. You could, of course, work this by partial fractions, and you would get equivalent answers. And then do pattern recognition, and this is actually what I was talking about with the student. So classify the integrand according to its form. So we have trigonometric functions. So if f of x is a product of powers of sine x and cosine x, or of tan x and secant x, or of cotangent x, cosecant x, then we can use substitution that we studied in a previous lecture about trigonometric integrals. If you have rational functions, ratio of polynomials, we can use partial fractions. If f of x is a product of a power of x, or a polynomial, and a transcendental function such as trig, exponential, or logarithmic, we might try integration by parts, choosing u and dv according to the advice that you had from this section on integration by parts. And I also included some notes about radicals. And so if you run across this, you want to think about using trig substitutions. And if you run across this, the nth root of ax plus b, you can use rationalizing substitutions u equal that nth root sometimes. And more generally, this works for the nth root of g of x. And then, and students don't like this one, but try again, because some approaches don't work. So if the first three steps don't produce an answer, there are only two main methods, substitution and parts, so try substitution again. You might have to be clever. I'll give you a clever example later. Try parts, and sometimes it is effective even on single functions. And so if it's an inverse tangent, inverse sine, and log, you can let these be u. Manipulate the integrand. A very common technique is multiplying by 1 in a clever way. This would be a difficult integral to do. But if we multiply by 1 in a clever way, we will get 1 plus cosine over 1 plus cosine. We're multiplying by 1. And then in the bottom, I will get 1 minus cosine squared and 1 plus cosine in the numerator. And this can be factored, so we can cancel that. And actually, we're not canceling it yet. I'm not canceling. I'm going to call this sine squared. And this is 1 over sine squared, which is the cosecant squared. I know how to integrate that. And dividing sine squared into that, I'm going to let u equal sine x, and I will get that. And then, another thing is, if you do a lot of homework and reread my examples and study my examples and read the examples in your book and study the examples in your book, a lot of those techniques you'll see it and you'll realize, oh, I've seen this before, I've done this before. So for example, if I asked you to integrate sine squared secant x dx, that would look challenging. But if you just use the trig identity of tangent squared x equals secant squared minus 1, this becomes two simple integrals, if you do remember the integral of secant, of course. And if you run across the integral of secant cubed x dx, we've done that about 5 times in this course. And so you say, oh, I know how to do that. In fact, you might be able to write the answer directly from your previous work. And sometimes you have to use several methods in sequence. Okay, so the following examples are offered. They're not completely solved, but certainly you could solve them. But often a good first step is the key. So I want you to look at it and start doing the problem. And the idea is, did you get off to a good start on the problem? So let's move to some examples. The first problem is the indefinite integral. This is tan cubed x over cosine cubed x dx. You know what to do. Let's see how you did. Well, to solve this, this is tan cubed times secant cubed. And so you see this is of the form where m is odd, the exponent on the tangent. And so the advice that we gave is that what you're going to do is that you're going to strip out a tangent and a secant and let u equal secant x. Alternately, what you could do is make everything into sines and cosines and end up with this. And then you could have continued with u equal cosine of x. Now you would have to change this cube into 1 minus cosine squared and strip out the sign. And then you divide and make the u substitution, and that would work. So you see there's a couple approaches on this problem number 1, or example number 1. Here's another problem, the indefinite integral of e to the square root of x dx. You know what to do. Let's see how you did. You just let u equal the square root of x, and that means that x equal u squared. So if x equal u squared, then dx is equal to 2u du. So this becomes the 2, this is u, e to the u du. And now what you can do is you can do integration by parts on this, and remember you have to change it back to x at the end of the problem. Here's another problem. This is the indefinite integral of x to the 5th plus 1 all over x cubed minus 3x squared minus 10x dx. You know what to do. Let's see how you did. Now there's no algebraic simplification or substitution that's obvious here, and so the big thing to do is to do algebra, and you just do long division. So you're dividing the cubic into the 5th degree polynomial, and eventually we'll have something that we can integrate relatively easily using formulas that we had before, and then partial fractions. Here's another example. The indefinite integral, this is dx over x times the square root of ln x. You know what to do. Let's see how you did. The substitution u equals ln x will work because this becomes the square root of u, and dx over x is du. The indefinite integral of the square root of 1 minus x over 1 plus x dx. You know what to do. Let's see how you did. You can make this substitution, but it's actually difficult. It leads to a very complicated rational function. An easier approach is to multiply top and bottom by 1 again, but this time I'm going to be multiplying by square root of x minus 1 divided by the square root of x minus 1. When you do that algebra, here I will get the square root of 1 minus x whole squared, which is 1 minus x. And in the denominator, I'm going to get the square root of 1 minus x squared dx. And I'll do this term by term. I'll divide the denominator into the 1 and the denominator into the x, getting this. This first integral is known to be the arcsine minus, and this you can let u equal 1 minus x squared, and work through the u substitution, and you get this plus c. Now I'm just going to say that you can't integrate all continuous functions. The answer to that is no. For example, you could think about, can I integrate this? And you'll never be able to do this. The answer is no. In terms of functions that we're familiar with, these are called elementary functions. These are called polynomials, rational functions, power functions, exponential functions, logarithm, trigonometric and inverse trig functions, hyperbolic and inverse hyperbolic functions. We are going to study these in Calc 2, but at COD we haven't studied them yet. And all functions that contain from these can be obtained from these from the 5 operations of addition, subtraction, multiplication, division, and composition. So here are some additional elementary functions. Now, if f is an elementary function, then f prime is an elementary function, but the integral of f of x dx need not be an elementary function. So, for example, we talked about this one, and since f where f is e to the x squared, so it's f sitting here. That's lowercase f is continuous. The integral exists, certainly, and we can define capital F this way. So we can talk about this thing, but we can't use the fundamental theorem of calculus to calculate it. And thus f of x equal e to the x squared. It does have an antiderivative, but it's not an elementary function. And no matter how hard we try, we'll never be able to do this. Later on in our course right now, we're going to represent this as an infinite series, and we'll have ways to do that. But we're not talking about that yet. The same applies here. So it's a pretty complicated subject. And sometimes it pays off just to be really clever. This is sometimes called the Weierstrass substitution. And this is a substitution for rational functions that involve sines and cosines. So for integrals involving rational functions, polynomials of sines and cosines, the substitution u equal sine x over 1 plus cosine x, or more general, u equal tangent x over 2 yields. The cosine is going to be replaced by 1 minus u squared over 1 plus u squared. The sine of x is going to be equal to 2u over 1 plus u squared, and dx is going to be substituted by 2 du over 1 plus u squared. Now, the proof of this follows from trig identities, because u squared then is going to be this squared, and the sine squared is 1 minus cosine squared. And if I factor this, I'll be able to cancel one of the 1 plus cosine x's, and I will get this result. Make sure you follow this. If I solve this, and you should do the algebra yourself, solve this for cosine x, you get cosine x is equal to 1 minus u squared divided by 1 plus u squared. To find sine x, write u equal sine x over 1 plus cosine x, and then we solve this for sine x and use our value for cosine x. I get that sine x is 2u over 1 plus u squared. And finally, to find dx, consider u equal the tangent of 2x. So that means that the arctangent of u is equal to x over 2, and dx is equal to 2 du divided by 1 plus u squared. This has been called by the great contemporary mathematician Spivak actually a very clever substitution. In fact, why don't we do one more problem? Evaluate the integral. The indefinite integral, this is dx over 1 plus cosecant x. You know what to do. Let's see how you did. Okay, this is going to involve the Weierstrass substitution. So we're going to let t equal the tangent of x over 2. And that means that x is equal to 2 arctangent t. I can differentiate this then, so dx is 2 dt over 1 plus t squared. And the cosecant is the reciprocal of the sine, so it is going to be 2t over, actually it's the reciprocal, so it is 1 plus t squared over 2t. So now what I'm going to do is I'm going to substitute all of that into this and simplify. And you should follow the algebra of the simplification. But what you will get at the end of this is the indefinite integral of 4t over 1 plus t squared times 1 plus t whole squared. And this, when I'm integrating that, this is partial fractions. This is the partial fraction decomposition. Now, this can be done by Heaviside cover-up theorem. Or actually, D can be found by Heaviside cover-up. But anyway, we end up with this, and so we have to do partial fractions. There are 4 equations in, 4 unknowns. that we can solve. So what we're going to get is, after we equate all the coefficients, we will get these 4 equations and 4 unknowns, which can be solved. So A is 0, B is 2, C is 0, and D is -2, which means the partial fraction decomposition of that is this. So again, there's a partial fraction decomposition. So the integral is the integral of that. I do the partial fractions, and when I do that, this is going to be 2 arctan of t. This is just a u substitution. It's 2 over t plus 1, and there's a constant of integration. Now I have to replace t with what it was, but t was tangent t over 2. But notice here you have 2 times. This is the arctan times the tan, so that really is just 2 times x over 2 plus these others. So there is your final answer. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.